Okay, good morning. Wow, that was not good. Good morning? Hey, that's great. Thank you. All right, so we're going to continue talking about convergence tests. And that's going to be the theme for the next few lessons, talking about how to find out if things converge. Today we're going to talk about what's called the comparison tests. So first of all, let's look at a series we've seen before. One over n squared. Okay, we've seen that a few times before. It's a nice series. Simple one. Okay, now question, does this thing converge? And how do we know? Yes. Why? Yes, good. Excellent. So this thing converges. Because it's a P series, right? With P being greater than 1. All right, so remember, as long as the power downstairs is greater than 1, strictly greater than 1, then this thing will converge by the P series test. And we saw the P series test last time when we talked about the integral test. This is a consequence of that. Okay, now let's look at a series that looks very much like that. If you look at 1 over n squared plus 1, this thing looks like 1 over 2 plus 1 over 5 plus 1 over 10 plus 1 over 17 plus 1 over 26 plus dot, dot, dot. So this is not a P series. It's also not geometric series. We could use integral tests to find out whether this thing converges or not. But another option is to compare to something that we know but looks very much like it. In fact, you could make the argument that when n gets large enough, this plus 1 is not significant anymore. So after a while, this thing is going to behave very much like 1 over n squared. So we suspect that this thing will eventually converge, right? Now we need a better argument than that. Notice that for all the n greater than or equal to 1, 1 over n squared plus 1 is strictly less than 1 over n squared. Just look at all these terms I have lined up. The first term, n is equal to 1. This one is 1/2, less than that. Second term, again, less than that one. And again, and then again. And because we know that 1 over n squared converges, and has a sum, whatever that sum is, that's not really that important at this point. But we know it's got a sum. And since all of these terms in my second series are strictly less than the first, we know this second series must have a sum that is smaller than the P series, right? You follow that argument? Whatever this turns out to be, it's got to be smaller than that because I'm taking away a little bit from each term. Has a sum smaller than that of 1 over n squared. So therefore, by doing this comparison, we can very conclusively and confidently say that this second series must also converge, right? So 1 over n squared converges. Okay, does it make sense how the argument went and how we can say this very, very confidently? Yep. So that's the basic idea of what's called a direct comparison test. So the idea is to compare two known series Okay, so name a couple of series that we know a lot about already. What's that? Harmonic, okay. And what do we know about harmonic? Right, it diverges. What else do we know? Another series that we know. Geometric, excellent. And it converges if what happens? Right. The absolute value of the ratio is less than 1. Okay? We also know the P series pretty well. Converges if P is greater than 1. In fact, harmonic is a P series, right? But that's a very useful one to know, and therefore it deserves to be mentioned on its own. So the basic idea you saw last time. If series we're looking at is less than or equal to a convergent series, then the series must converge. Right? The last example, we saw one case of that. If a series is greater than or equal to a divergent series, then the series we are looking at must also diverge. Divergent series has an infinite sum. If at least one term is bigger than that, then this new series must also diverge. If series we're looking at is less than a divergent one, so we're comparing, for example, a new series to a harmonic, and we found out that the new series has terms smaller than a harmonic. What can we say about that new series? Actually, all of that is possible, right? Because this divergent series has an infinite sum. So the new series might have a smaller infinity as a sum or a finite number. So we can't say anything about it. It's inconclusive. Same thing if a series is bigger than a convergent series. Again, we cannot say much about it. if we find a series that's got terms bigger than a P series, it could be another bigger finite number or infinity. The first two are the most useful things we can say. All right, so let's look at a few examples. And the most difficult part about this kind of test is to come up with what to compare to. So we'll focus on that. Before we do anything, what's the first test we always want to use? The divergence test, which says what? Yep. First, we check what happens when n goes to infinity. If this thing does not go to 0, then we say it diverges, and we're done with it, right? And here, of course, we see that this goes to 0. So therefore, this thing has a chance to converge. Okay, we're going to use the comparison test to draw a conclusion, but this is also one that you could use an integral test to find out what's going on. But normally you have your choice of what method to use. Today we're going to focus on the comparison. All right? So here's the question, what to compare to? One thing that always works is to see what happens when n is sufficiently large. Right, look at the first example I gave you. Remember I said when n is large enough that +1 is irrelevant. Therefore, it'll resemble a P series here after n is large enough. That's the kind of thing you want to continue doing. If n is large, n over 2n squared minus 1 is roughly equal to n over 2n squared, which is roughly equal to 1 over 2n, right? So this means that the series we're looking at is going to behave like 1 over 2n eventually. All right, so now we need to know what happens to this thing. Does 1 over 2n converge or diverge? If this 2 is not here, what would you say? Diverge, right? What does that 2 do in terms of conversion? It changes the sum, but it doesn't change the convergence property. So remember, 1 over n, this thing has an infinity as the sum, right? If you divide infinity by 2, that's still infinity. The constant multiple does not change the convergence property. So this thing is going to diverge. Okay? Now, if we can show that these terms are bigger than the divergent series terms, then this has to necessarily also diverge. Oops, sorry, I got this switched around. Right, we need to show that this thing has terms that are bigger than the terms in this divergent series. If so, then that has to diverge too. So is this true? What you could do here is to do this. I could multiply the second one here by n on the top and the bottom. Now is it easier to compare? Is this bigger than that for all n? Yeah. Because? How do you know? Besides plugging in a bunch of n's. Yeah, it's got a smaller denominator, right? Yes, because n over 2n squared minus 1 has smaller denominator. A smaller denominator means a bigger number when the numerator is the same. 1 over 3 is, let's see, 1 over 2 is bigger than 1 over 3, right? It's got a smaller denominator, so it's bigger than the other term. So now what's the conclusion? Does this thing converge or diverge? We established that all of these terms are bigger than a divergent series. So therefore, diverge, right? Questions? Nope? Okay, so that's the basic idea of that. Let me show you another test that's very closely related to this test. The basic idea is the same, is to look at what happens when n becomes large enough. That's when the comparison will start to matter. And this test is called the limit comparison test. So we have a series that we want to know more about, summation an here. When you look at this new series, just like last time, you think about a series that looks like it that we can compare to. But the way we're going to compare is slightly different, is to use the limit. So you do the limit of the new series over the known series. When you take the limit to infinity, if this thing turns out to be a positive constant, then your new series converges if the known series converges. So in other words, if the limit turns out to be a positive constant, then these two series either both converge or both diverge. And this works because of this constant here. A positive constant means when n is large enough, these two things behave more or less the same, that one will be some constant multiple of the other. And we know constant multiple doesn't change the convergence. So if this thing is true, then eventually the tail ends of these two series will look very much alike. And then we can use that to make a conclusion. Okay, so let's try this on the last example we just looked at. So here's my AN. And the known series I'm comparing to is the harmonic series. Now I take the ratio of the series in question over the known series. So I get this, and when n becomes large enough, that minus 1 is irrelevant, so we get a 1. And that's a positive constant. So therefore, by the limit comparison test, this positive constant tells us that they will look alike after a while. Therefore, they will both converge or they will both diverge. And because this thing diverges, the series in question also diverges. Okay, so that's how the limit comparison test works. One is, they're related, right? One is a consequence of the other in a way. You need to know both of these methods because sometimes one will fail and the other one will give you the answer. All right? Okay, let's do more examples. One plus sine of n over n cubed. Again, what's the first thing you want to do? Yep. So that's what we want to see. Is it true then? Does this go to 0? What does sine do? It bounces between 1 and positive 1, right? So the numerator can be no bigger than 2 and no smaller than 0, right? So the numerator is bounded, but the denominator keeps growing. So therefore, this will eventually go to 0, right? So yes. And that means we have to check further. Okay? Now let's think about what we can compare this to. I kind of told you what to compare to already. When n becomes large enough, sine is just bouncing between plus and minus 1. Right? So 1 plus sine of n is no bigger than 2. Knowing that, what do you think is a good series we can compare to? Yeah, that sounds like a good idea here. So therefore, we're saying that this thing is at most equal to that, but typically less. Does this converge? Yes. Which converges. Okay? So now we need to show that this thing is smaller than the terms in a convergent series. And because we know sine is bounded between minus 1 and 1, and the numerator is bounded between 0 and 2, whatever the n is, this thing is always no bigger than that, at most equal. In fact, most of the terms in here will be smaller than that, right? So therefore, this series here must also converge. Make sense? Okay, every term is less than the a convergent series, so this new series must have a smaller sum, and therefore it must converge. Let's try the limit comparison test on this. You put a numerator. Numerator is the series in question, which is 1 plus sine of n. Denominator, we put the series that we know everything about, which is 2 over n cubed. Whichever test you choose to, whichever version of the limit test, of the comparison test you choose to use, you still need to know what to compare to. So that's the key part of this kind of thing. Okay, now we look at the limit of 1 plus sine of n over 2. And what's the limit? N goes to infinity. So what's the limit? Does not exist because? Absolutely. So this number is always between 0 and 2, right? Depending on what n is, it's somewhere between 0 and 2. There's no limit there. It doesn't matter how far you push this thing to. There is no limit because sine doesn't settle down. So this does not exist. So you see here, the limit comparison test is inconclusive. This happens all the time, that for a given series, one of these two versions of limit of comparison test will be inconclusive. So here, the earlier direct comparison gave us a conclusion, but the limit comparison fails to tell us anything meaningful. So that's why you need to use both tests. Question? Okay, let's do more example. We got to get used to the idea here. All right, so we got n over square root of n squared plus 2. So I want you to take 1 minute to think about what to do with this series. If you can come up with a conclusion, great. But if not, at least think about what steps you would take to find a conclusion. So 1 minute. Okay, that's 1 minute. Who can tell me something about this? What would you do? Let's start with you. Okay, good idea. And what conclusion would you? And what's the conclusion then? Okay, what do you think?
Well, if you spread the top and the bottom and then take the limit as n approaches infinity, then you get 1.
Yeah.
So that's divergent.
Right, so it fails the first test I tell you to check all the time, right? So what he said is absolutely true. You can compare to something, but remember, I keep telling you the first thing you want to check, first test to use is always this one. Because that's a simple test. If it doesn't go to 0, conclusion is right there. It diverges. Done. We move on, right? So here, what do we get? We get 1. When n is sufficiently large, the plus 2 is irrelevant. So we have n over square root of n squared, which is n over n, and it goes to 1. So diverges. Right? Quick test. And you're going to learn a few more tests later. Don't forget this very first one. Later on, you'll learn a few pretty powerful tests. Don't you know, they're really nice. They're really, really cool. But don't forget this simple test. That's always the first one you want to check. If you don't check that, that's okay. You can still get the right conclusion, but you might be doing a little bit more work than it is required. More examples. Three to the n over 1 plus 4 to the n. Okay, this time I will give you 2 minutes to think about what to do and think about what to compare to. 2 minutes. Okay, that felt like 2 minutes. All right, does it pass the divergence test? Yes. Okay. Right, when n is large, 4 to the n is so much greater than 3 to the n, and on top of that, you're adding 1 to it. So this thing is going to be dominating, therefore it goes to 0. So it passes. Okay, now give me some idea of what to compare to.
Well, since there's the angle of the too large, the one basically doesn't matter.
Right.
There's 3 and 1.
Compared to this thing?
Yeah.
And what do you know about this? Good. Excellent. This is a geometric series. With a common ratio 3 over 4, that's strictly less than 1. Right? So this thing converges. Well, the geometric series converges. And what we need to do now is to demonstrate that these are smaller than that for all the n's. Therefore, we can say this will converge too. Well, that's pretty easy to see. This thing, again, for the same numerator, this thing has a bigger denominator. So this is always smaller than that, right? So therefore, this thing is going to what? Converge. Good. All the terms are smaller than a convergent series. Therefore, it will also converge. Right? You have two basic families of series to compare to, geometric and P-series. Always think about one of those two. Here's a question. What if I change the starting n to like 5? Does it change the convergence or divergence conclusion? No. Why not? Yeah, I just left out 4 terms. So if this thing has a finite sum, I took away 4 finite terms, that is still going to converge, right? But the sum is going to be different. So this will still converge with a different sum. So if this were a divergent series, then changing the starting index, again, doesn't change the fact that this will diverge. You're taking away or adding more finite terms to something that's either infinity or finite number. That doesn't change the convergence property. So all the examples you've seen so far have the starting n at 1. That's just purely for convenience. We can start at any n. So don't let the starting n get in the way. What you do is still the same. Okay, let's try this one. This one is fun. 1 over n times e to the minus n. Okay, 1 minute to check the first test, and then think about what is a good thing to compare to. 1 minute. All right, so does it pass the divergence test? Yeah, yes. All right, so good news, it passes. Bad news, you got to do more stuff, right? So okay, let's think about comparison here. What's a good thing to compare to? Let me hear from you. 1 over e to the n, okay? Any other suggestions what we can compare this to? Okay. Any other suggestions? These seem like reasonable ones to think about. Okay, so let's look at the first one first. What do we know about this series, 1 over e to the n? Yeah, you suggested, so tell me more. It converges because? Good, excellent. So that's a convergent geometric series. Second guy here, this is a divergent series. Divergent harmonic, that's redundant. Of course it's divergent, right? It's like saying a straight line. A line, of course, is a straight thing. So anyway, you get the idea. So what we need to do here is to show that these guys are smaller than this, or these guys are bigger than that, right? Let's look at the first one here. Is 1 over n, by the way, if you wonder where that came from, e to the minus n goes downstairs and becomes e to the n. Okay? So is this smaller than that for some n? Yeah, for which n's? What about 1? 1 is equal, right? Equal is okay. So yeah, n greater than or equal to 2. So the first terms of these two series are equal. That's okay. You can simply throw them out and compare the rest, right? But for n equal to 2 or beyond, this is always smaller than that. So therefore, this thing is going to converge because the terms are smaller than a convergent geometric series for some n, and the one we left out is equal. That doesn't change anything. Okay, now looking at this other one here, because that thing is a divergent series, it doesn't make sense to see if these things are smaller than that. Something smaller than a divergent series doesn't tell you anything, right? So we need to show that these are bigger than that. Well, that's clearly not true, right? So no. So therefore, the terms are no bigger than a divergent series. That doesn't tell us anything. That tells us basically anything could happen at this point. So if you use this test right here, we cannot conclude anything from that. All right, questions? Yeah.
So when you have from n equals 1 to infinity, you're adding the term when n equals 1. Does that just make it divergent? Because it seems like it's still converging just because.
If this is 2 to infinity, that is going to converge. And
If it's 1, it seems like it's still converged just by the.
we're adding a finite term to a convergent series, so that doesn't change the convergence property. So you're right. The whole thing is convergence. Yeah. Okay, that's it for today. Have a good weekend. See you Monday.